Okay, we can start now. So, okay, my monitor is not working, it's blank, so I have to look at the back to see what's happening. Okay, so what we are going to do today is introduce you the concept of free body diagrams. That is very important concept-wise because that will lead us to the analysis and also by looking at the equilibrium of the whole structure or the object, whatever it may be, or part of it. Now let's go to some examples. So what is a free body diagram? Now it's sort of a sketch showing all the forces that act on a body. And on a body, that is an important one. That means the body that is of your interest. So there could be a number of free body diagram you could draw, and that will depend on what you are trying to solve at that point or for that particular part. The term free here means that all supports have been removed and replaced by an appropriate type of reaction forces. So to give an example, which is from the introduction slides, that imagine you have got two columns supporting a beam, like a Stonehenge type of structure. And then there are some loads onto the beam, on top of it. Now, if you want to analyze the whole system here, including the beam and the two columns, then your free body diagram would be looking something like this in here. So you draw the beam, you draw the columns, and then what you are removing here, you are removing the ground from there. So replace the representation of the ground by a reaction force, suitable reaction force. Now, of course, you don't know which direction this reaction force would be. It does not matter. You put it in an appropriate direction you think that it is going to be. And once you do the calculations through equilibrium, if your direction chosen was correct, it will come up with a positive value. If the value comes with a negative one, that means it's a direction that you have assumed originally that has to be reversed. So we replace the ground by these two equal forces, but also we put the load that was acting on it. So that will give us what would be the load onto these columns by considering the equilibrium of this whole system. You may not want to do the whole system. You may want to find out what about the beam itself. How does it bend? Now, of course, the beam is supported on these two columns. So you strip those supports and replace by two reaction forces. Okay? So this is the free body diagram of the beam. So this is the free body diagram of the whole system, free body diagram of the beam, and these two shows free body diagram of each of the columns. So if you consider the free body diagram of the left column, of course it is supported by the ground, so it would be a reaction force possibly there. And of course at the top the beam is possibly giving some load onto it, so you'll put a load in there. Now, how much of these loads would be the green one or the blue one? You have to go back to the equilibrium. So you cannot readily find out how much is this reaction forces. So you may have to do equilibrium of different parts or the whole system as you want, as it is required. So this process would remain the same for any problem that you will be doing. And we will be doing lots of examples like those. But I'll also go into little bit more detail into free body diagram today, and then we'll solve some problems, time permitting. So, first of all, let me, this will be probably a little bit complicated. Let me draw a free body diagram of the bottle and the holder system. Okay. So can you see it from there? Yeah. So if I want to draw the free body diagram of this case, so how should I approach? Let me put the visualizer on. Okay. So the free body diagram of the whole system, so if I am doing as I am seeing it, so you have got the stand, and then you have got the bottle as well. So the bottle is somewhere here. Maybe slightly thicker and extends beyond it. So it's not to the scale, but this is something like this. So probably not very right because it doesn't go through there, but it's only the inclination bit. Let's try it slightly better. So it is something like this. So this is the bottle, and the holder is something like that. Okay, so if I want to do the free body diagram of this case, how do I do it? Now, first of all, I have to think about, so what I have done the free body system, free body of the whole system. So there are two objects. So object is you have got the bottle here, and you have got the stand there. So there are two objects. And of course there was a ground in here. So the ground is in this case the top of the table. So ground must be giving our reaction forces. Okay, so and this bottle and the stand, they do have their own weight. So probably bottle center of gravity we can assume probably about the middle of the thick part, so somewhere there maybe, or maybe slightly on this other side by looking at it. So it could be, so this could be weight of the bottle. For the stand, again nearly half of the length here, so that would be weight of the stand. So that needs to be, these two weight needs to be balanced by the ground reaction force. So that's a first set of free body diagram that we can think about this whole bottle and the stand system. Any other forces that we may be missing? Sorry? Go on, I cannot hear. Be louder, please. Gravity of what? So gravity pulling the bottle is this weight. So that is WB. Gravity pulling the stand is given by the weight, WS. Is that okay? Yeah, go on. Yeah. So those things are internally balanced at this moment. You mean at this joint in over here. So if we are doing the whole system, then possibly we don't need to bother about that at this point. But what we need to consider is what would happen if this was not on a surface like this, maybe on table of ice, for example, or in other words, no friction. So there is a possibility of a friction force. Now we don't know the direction, so could be this direction or could be other direction. But so that there could be a friction force in here. So could be a friction force. But other than that, these three are the main forces in here that is acting. So the weight, Ws, and the reaction force, and Wb and Ws. So if you do the vertical equilibrium of all the forces, so summation of vertical forces 0, if you write, so summation of vertical forces 0. That would give me that the force going up, R, is equal to all the forces coming down, which is the weight of the bottle plus weight of the stand. Now, if you can measure the distance, if you know the position of the center of gravity, for example, if you know where this is, or in other words, if you know this distance, so let's say this is d1, and let's say this distance is d2. If you know these two distances, for example, you can write a moment equilibrium equation as well. So you can also write a moment equilibrium equation. So moment equilibrium equation would be, so if you take moment about the support point here, so the bottle would try to rotate the whole system in the clockwise direction. So the moment for that would be Ws times d1, and the stand, its own weight, will try to rotate the whole system in the anti-clockwise direction. So minus Wb times d1 minus Ws times d2 would be equal to 0. So if you know d1 and d2, then you can get a relationship between Wb or Ws. Or in other words, if you know what is Wb, Ws, then you can get d1 and d2. So you can find out sort of center of gravity. So in other words, if you weigh this bottle, how much does it weigh? And if you find out the weight of the stand, and if you measure the distance of this stand, which is fairly smooth one, except that hole, then you can find the center of gravity of the bottle, for example. So these two sets of information here will give you the things you need, for example, location of center of gravity, positions of those center of gravity for the stand or the bottle, if you do some extra measurement. Otherwise, this information doesn't hold much. So this is probably the main one that you need. Now somebody there asked me about what about the bottle. So this is for the whole system, free body diagram for the whole system. Now what about the bottle then? So if I want to draw the free body diagram of the bottle itself, how do I do? Now of course I will draw the bottle itself first. Now that will not be exactly the same bottle, I can guarantee you. So this time even a better one. So that's the bottle. So we know the force acting on it, so which is the weight of the bottle. Now under that one, it is of course not under equilibrium. So if you do summation of vertical forces 0, then of course it will show that there is unbalanced force. Now the bottle is supported by the stand at this point. Now, so the stand must be giving a reaction force in this direction. So this is the reaction force from the stand. Okay? And it has to act opposite direction. So by looking at it, I could say RS is equal to WB. Now, is this balanced? Or let me put it in the, is this under equilibrium? So I am drawing the free body diagram of the bottle. I put the weight of the bottle, that's the only force acting on the bottle due to gravity. Now that must be supported by, there is also a support from the bottle here, a stand here. So the stand must be giving an upward reaction force to get the bottle under, to resist the weight of the bottle. So if we do that, then RS is equal to WB, and I say that's equilibrium. Is that correct? No, go on. Yeah, very good, because if we consider these two force systems, this is not under equilibrium. Yes, RS is WB, that is fine. So vertical equilibrium is maintained. So if you do summation of vertical forces equal to 0, then that's a big tick mark. But what about the rotational equilibrium? So the bottle as a whole will not move up or down, true, but under these two forces, equal and opposite, it could rotate. So moment equilibrium is not equal to 0. So this is not under equilibrium. Sorry, you need to remind me if you don't see that. So this is not in equilibrium because it can rotate.
Doesn't the stand have an upward force near where the net is and near where the top is with downward force?
So there must be something more complicated going on here. Absolutely right. So the actual one would be, if you look at, if I can show you here, so it's slightly oblong shape. So if I put the bottle in here, then if you think about going into according to this diagram, so the bottle tendency, if I hold it, if I giving a support here, the bottle tendency would be to rotate. Rotate means going down in this direction. That's what it would mean. The bottle would go down there. But of course, it is supported at the top bit. So the top part here will put our reactions downward. And the bottom bit here, so this part will give you the forces upward. So a revised diagram of free body diagram for the bottle could look something like this. So you have got, again the bottle, you can write down. So you have got this bottle, you have got this weight WB, and then instead of this this single reaction force, I will have a reaction force here, let's say R1, and on the other end that will try to push these things by R2. So there will be two forces acting onto from this stand reaction point. So this point here, that's where the bottle is resting. So that will give you an upward reaction force. So the whole weight is resting at this point. So that will give us upward reaction force. But the top bit here is crucial, because imagine if there was no top part here, its center of gravity is there, you are resting it in here. Say if there is nothing here, then it will simply go off like this. So the top bit here is holding it down. So it is providing a it is resisting the tendency of the bottle to rotate in this direction. So it must be giving a force in these directions to keep it horizontal. So that is the role of this R2 in this point. So the R2 is trying to push this bottle in the opposite direction. So this is now a sort of an equilibrium. So you can now say vertical equilibrium wise, you could say R1 is the only one acting upward direction. So R1 would be R2 plus WB, weight of the bottle, plus this. So the actual reaction force from the stand is 2 bit. So R1 and R2. And the moment, so if you take moment about point R1, so moment about take point 1, so if you take moment about point 1 equal to 0, then you should get that WB is creating an anti-clockwise moment. So let's say this distance is say C or B1 for bottle, and this distance is say B2. Then the so the moment due to WB would be WB times C1, that's clockwise moment. That must be balanced by the reaction force from the stand. So that is minus R2 times C2 equal to 0. So now there is depending on the values of R1 and R2, of course, this is okay from the equilibrium. So if these two equations are valid, then the bottle system and the bottle on its own is under equilibrium. So if I just quickly go through this bit, because that is quite interesting here, because if you don't know anything, for example, you could start with there is one reaction force there, and you'll quickly realize that one reaction force is not enough. So either it may be two reaction force or some form of a moment must be given as a reaction force from the stand, and that would keep it under equilibrium. So this is the free body diagram of the bottle. Again, as before, reaction force is equal and opposite in nature. So I said that because if we now draw the free body diagram of the stand, then you could use the bottle free body diagram and draw the stand equilibrium, stand free body diagram. So if you draw the stand, for example, free body diagram of the stand, so if you draw the free body diagram of the stand now of course near about the middle it has got its own weight. So that is weight of the stand. And at the bottom it has got the reaction force from the whole system you have calculated before. So that is R, which we know is equal to WB plus WS. That does not change. WB plus WS, that does not change. So that's from the top. Now of course in here now we will have two other reaction forces that is coming from the bottle, and it would be equal and opposite. So R1 was the reaction given by the stand. Now of course you can imagine R1 is the near end where the bottle is giving its weight. So the action of the bottle on the stand at this point is giving an weight in this point. Okay? So the bottle is dropping its weight at this point, and that would be value of R1. And at the further point R2 is that it was giving an upward reaction. Bottle is trying to put the stand upward. So at this point then it would be R2 in this case. So you could see that they are equal and opposite in the direction. So R1 is upward on the bottle, but R1 is downward on the stand, because that's the action or the weight of the bottle in this case on the stand. And R2 is the force that bottle would provide onto the stand due to its rotational tendency. So that would then complete the free body diagram of the stand itself. Now you cannot possibly find out all these values R1 or R2 if you just do stand. So you may need to find out the values of R, you may need to find out these equations. So to solve the whole system, you may need to do a number of free body diagrams to get the complete picture. Is that okay? Anybody did not understand any point in here? Yeah, go on.
I understood most of it, but I feel like wanting to tell myself a bit of a reiteration. So using the fossil free body diagram is the best thing to do here. So all you have to use the object that is the largest.
So your question is, why do we need to do 3 separate free body diagrams? Is that correct?
Yeah.
Okay. So if you are interested in, for example, as I said, if you did just the system one, that will give you certain amount of information. For example, if you have measured, for example, you want to know the centroid of this bottle, for example. Where does the center of gravity for this bottle is? If you know the center of gravity for this stand, then measuring couple of distances, you can find out by using this equation. So it will serve you that purpose just by doing that. But if you want to see how much forces is going on to this neck of the bottle, for example, for the moment, then that will not serve the picture. So you need to then do this bottle's free body diagram coming here, then that will tell you how the force varies onto the neck of the bottle. For example, there will be nothing from here till the end of the bottle except its own weight, but between here there will be a moment and a shear, for example. So it all depends on what you're trying to analyze, and that is the level of detail of the free body diagram you have to go into it. So as I started, free body diagram is not a unique one. It depends on the problem that you are solving. Is that okay?
Yeah.
Is that okay for everybody? Okay, go on. In this case, I have taken clockwise moment positive, but I'll talk about sign convention later on. As long as you mention what is your sign convention, anything is fine. If you say anti-clockwise is positive and you are consistent, at least in that problem, that's fine. But you have to state that this is my sign convention. Okay. So that was one example, how we are doing in terms of the time. Okay, we have got, okay. I'll stay with this free body diagram a little bit longer. I'll try to do another one, which is, of course, you do use it regularly, which is a pair of scissors. Okay, so a pair of scissors, a very everyday object, but free body diagram of this pair of scissors is anything but straightforward. So what a scissor does, a pair of scissors does, it cuts through things. So you put in things there and you try to cut it. Okay. So if I show it from this view, this would be exactly what you would be looking at. So in the diagram there I have shown is with probably this view I have shown, but anyway. So I'm putting a force through my fingers here, thumb and the other fingers towards each other. So I'm putting a force in these directions in here. And that force through this lever is getting transferred to the object that I want to cut is in this direction. So I am putting a force going towards each other, and through the lever as they cross each other two blades, then that is giving a force onto this object over here, and by that it cuts. Now, what would be the free body diagram if I ask you? So you are a designer of this pair of scissors. You want to know how much force or what is the material width. I mean, if you have to cut a tree branch, for example, which is 20 millimeter thick, can you do it with this? So would that have enough strength? And more importantly, would the rivet would be strong enough? Often in these cases, this is the weaker point. So hardly the blade fails. Normally the rivet fails for this joint in here. So you want to design the whole scissor. You will see whether each and every part of this scissor would hold together if you want to do this cutting action. So let's look at the free body diagram. That's where we want to start to look at the forces acting due to this cutting action. So that's my scissors, pair of scissors over here, as you can see on this. So as I mentioned, two forces acting on the handles in these two directions, and that forces is getting transferred onto this object in the same direction. So the forces on this object is in this direction. Now if I remove that, that's the free body of my scissor. So by removing this, what did I remove? The force that the scissor was putting in here. So it must be balanced by equal and opposite reaction forces. So in the diagram there, you can see those forces are primarily the forces that is given by this object that was undercut over here, for example. So these forces is getting into this direction. It is giving the same forces in this direction. So if I remove that, of course, equal and opposite reaction force. So at this point, so I'm putting the force in the directions of my finger. Same direction the force is in here. So free body diagram of the scissor means I want to take off other action. This is not important. So the scissor blades are giving forces in this direction. If I remove that, that was giving an equal and opposite reaction to the blades in the other directions. So that's what that diagram is showing. So that is over the whole two pairs of or these two pairs of blades in or two blades in here. Now if you take the left hand blade separately, which is this blade over here, and the right hand blade separately, and also the rivet which is connecting in there in the middle, then the free body diagram would be like the one shown. So you will have in that case, okay, the forces from the object that was undercut on the going towards the left on the left hand blade, going on the right hand blade to the right on the right hand blade, and the forces that I am applying in here remains the same, of course. Now if you consider the each blade separately, so the rivet must be putting that under balance. So the rivet must be on the left hand blade, give a force going from left to right to balance the two forces that is acting on the right to left. Similarly, the rivet must give a force from right to left on the right hand blade to keep it under the equilibrium of the forces. Now of course in this case I am assuming all the forces are horizontal. Okay, so that's I am assuming that by now of course this may not be completely horizontal, but this is assumption that this is horizontal, and it is to some extent true, because if the cutting forces is here also in the horizontal direction, then the forces is which would be equal to those cutting forces would be horizontal. So the rivet is then under equal and opposite forces. That's well and good. Can you design the rivet then? Can you design the rivet for this force? Yes and no. For the blades, probably these are okay. You can do that way. But if you ever look a scissor very carefully, you will see that each of the blades are not straight. They are ever so slightly curved. So that always you will see, if I try to cut, the joining edge always touches each other. So this is ever so slightly bent. And similarly, this touches on the between the rivet and the handle as well. So there is a pressure between the blades, so on both sides of the rivet. So on that side as well as on the between the handle and the rivet. So that is shown onto this diagram on the right over here. So if you consider the left hand blade, so this diagram is exactly showing the scissors in this view from the side. Okay. So you will have, so the forces on the left hand blade at the top above this is due to the two blades touching each other. So two blades starts to compress each other. Otherwise, it will not cut. You may have seen that when the rivets get loose, it's very difficult to cut. You have to then put a force sideways on the handle to make these two ends stick together, to make these two blades touch each other, to compress each other. Then only the cutting actions would be effective. So the top bit of the force in there is nothing but this compressive force between the touching force between the two blades. And as I said, the similar touching force is, if you have got a pair of scissors, you can, in your pencil box, you can use it. But when you go home, you can see that there is a compressive force between these two sides as well. Now, what it does to rivet? It gives rivets on the left hand side a force in the length direction. So there is a force acting in these directions of the rivet. So which is shown in this case here. So if you see the rivet now from the top, this is the left hand blade is at the top. So this puts a force in this direction, and that is the right hand force, right hand blade that puts a force on the rivet on this direction. So which is different, because originally when the rivet was in this direction, so you get a force acting into that directions because of these cutting actions. Now when it is in these directions, you will get two forces acting opposite to each other, and acting opposite to each other in this view. So the left hand one, which is this circular handle, will put a force half of the part of the rivet in one direction and another part in the other direction. So if you consider, you have got a force in this direction and a force in the other directions inherent. Now this is not under equilibrium, so it needs to be a force must be acting due to the friction onto this other bit. In total, the rivet also experience a splitting force in this direction. So by the cutting action, the rivet here not only experience forces in these directions of the object that you are cutting. So if you are cutting these objects over here, a rivet will experience a force in this horizontal plane, but also, it will experience a tensile force between these blades in this direction. Or in other words, the forces that will try to separate these two blades apart, or there will be tension in there. That's why these rivets, when get loose or slack, it doesn't cut. You have to artificially make these stick together by putting a forces into this handle sideways so that they stick each other. So as you can see, free body diagram often gets quickly complicated. So many forces act on them, and it all depends on what you want to do with it. So if your whole purpose was to design this rivet for some cutting action on a pair of scissors, these are the sort of level of force that you have to go into it. It's not an one force, two force, one moment, etc. So it all depends on what you are trying to solve. So free body diagram, again I remind you, is not a unique thing. It depends on what problems you are solving and the level of detail that you are getting into. But this is a great tool because unless you do a free body diagram, you cannot apply the equation of equilibrium effectively. And equations of equilibrium are the first step to analyze a response to the forces or action to the forces, for example, to any object. Okay, so this bit is there this diagram is there in the notes and everywhere. So you by all means look at it. If you don't get it, then ask me. Then I'll try to see another way how I can explain it. So the forces in a single plane may not remain in a single plane the way they interact. As you can see in the rivet, the forces were acting in this plane, horizontal plane here, due to the cutting action. So due to cutting action, the forces are all we assumed in the horizontal plane, but we could see the way they interact, and due to one blade above another, and that will create a force in the rivet in the perpendicular direction as well. So which will try to separate the two sides of the blades in the connections over here. Okay, so any questions on this one? Yeah.
I had a question. Can we optimize the performance of the scissors using a free body diagram, and is the current shape of the scissors optimized, or is it arbitrary to accommodate our hand?
So if that's your exercise, of course you need to go into that whether this angle are fine or not. But this would be the equilibrium and the free body diagram would be the first step to that. You cannot do an optimization exercise without going through that process. So of course the other bits will to come into picture, like ergonomics, for example, how easy it is to hold that one. So the shape of the holes, for example. So you want to put two fingers there and one finger there, for example. And then the span between your fingers and your thumb, for example. So all these things will come into picture. But of course, any first step to do a proper analysis would start with free body diagram with the structural analysis. But the design, the ergonomic side of this thing is separate. That's how comfortable you are in using this piece of equipment. So if you're thinking about optimization from that point of view, that's separate. But optimization from the use of materials, whether this shape is effective for cutting, for example, whether to cut an object, a rivet would fail, for example, or you need to put more tension into this rivet, for example, to do the cutting. These are the questions that you will be answering. This scissor, whether that's a perfectly optimized scissor, I don't know. There could be various other scissors in there. And this is not the only shape of the scissors. Right? You have got in your pencil case scissors of different shapes. So that as I said, that comes for different practice. So this is very awkward shape to keep it in, for example. A straight one probably better to fit in the pencil case. So there are all sorts of other competing interests people put it in here. But whether that will act as scissor, whether it will hold together to cut the thing, to do its job, that's the structural mechanics point of view. Yeah.
Well, on the free body diagram up there, the scissors on the top left, they show by the blade the result force because of the deflecting pressure on the object. The result force is going that way. Why does that not mean that on the handle, because there's force being made by a hand, which inwards the result force is the opposite way?
So it is in here. So just I think what you are trying to say is this is the top bit is the left hand one. So that's why you are see that over there. So I'm putting the forces in here in this direction.
But the result force is then pushing it back that way.
No, this is the force I'm putting it in there.
Yeah.
So my finger, so this is then effectively I'm putting the force. So if I draw the left hand, so that's the, let's say, left hand one, for example. So I am pushing it, I am putting a force in this direction. So that is my force, and it is trying to cut it in these directions. Okay. So at this point, it is trying to put a force in this direction. So reaction is in this direction. So only thing I am removing here is here. So that's why the reaction force is the opposite direction. Force is not opposite direction because I am giving the force in that direction at that point there. So the free body diagram is I remove that support or the opposite here. So this bit I have removed, and you can imagine my finger is still there in this case. But this one would give my finger an opposite direction force. So if you are interested in what forces I am getting on my finger, that would be opposite to that direction. Yeah. So it's sometimes Newton's third law is very easy to say, equal and opposite reaction, but it's very difficult to get it in when it applies in practice, which is action and what is reaction. Yeah. So be careful about it. Yeah.
Won't that force on object be oblique? Is it horizontal?
Yeah, that's what I said. My assumption. So I'm assuming here that all the forces are horizontal because the cutting action is primarily horizontal. But you are absolutely right. If the forces could be in the angle. Yeah. Yeah. But that would even complicate the process. So even with the horizontal assumption, we get into so much detail to get the forces on the effect. And with the oblong forces, it will be slightly more complicated. Any other question? Okay, so in terms of the time, we are doing very badly. So what I suggest you to look at is there is another examples here. So try to do this example. So the next Thursday, isn't it? Thursday we have got lectures. So please try to do these examples, and then I'll go through this, try to do these examples, and I'll go through all these examples on that day. This one we have done. This one is, we have slightly different version of this. So this is not a symmetric problem. Same one that we have got these cables at 5 meter, 10 kilonewton load. Now there the two angles are slightly different. So find the load into each of these cables. The third one, again a variation of this, I put another member. So 3 members in there. This one we have done, not completed, but complete that. And this example also you need to have a look at it. So please go through that. I'll be doing these problems on Thursday. Okay? So if you have got much better that if you think about it, that how to solve this problem, and that's where most of your effort should be. That if you are given a problem, you should be able to see or think about how to tackle it. Okay? And then I'll go through the other things. Thank you. Yeah?
My notes are good enough. Because you're the person I've been writing.
Let me wear my tie. Let me wear my tie. I do need to come close to you, yes? Yeah, yeah, yeah. Yeah, you can get that on the podcast. Yeah.
Yes, thank you.
Good.
So basically on the right track.
And if many of you say that you had difficulty, then I can put a little video to that if the podcast is not sufficient.
I have a question about this one here.
Yeah?
I was just wondering, if R1 is equal to R2, I don't understand how, where's the weight of the bottom?
R1 is not equal to R2.
Oh, right, okay.
Yeah, it won't be equal to R2. So R1 would be R2 plus the other one.
Yeah, okay.
Take a photo of what you saw today and put it on Blackboard.
Do you want that? Okay.
Thank you, sir.
Yes, this is working.
No, it's not working. I had to look at the screen. So we need to report that. Coming on and off. Not that it's not working.
Ah,
It comes on and off. So it must be something.
it's a dodgy connection. Oh well. You okay?
Not bad.
It's like, it's weird, right? It's still
Today I talk about free body diagram. Save. I think it's going to be the connections there. PC. Yeah, because it's coming on and off.
well. Sorry. I might
I have to look at the main.
use. Morning, you right?